Hi, my name is Yucheng. I'm a master's student at ETH. I'm going to talk about our paper, Private Distribution Testing with Heterogeneous Constraints. This is a joint work with my undergraduate supervisor, Clément, at the University of Sydney. This talk consists of 5 parts. First, I will give a brief introduction. Then, I will introduce the models that we focus on in this paper. Then, I will introduce the results we obtained in this paper, as well as the corresponding algorithms. Lastly, I will give a summary to our results. Okay, so what is closeness testing? This problem has been studied by statisticians since over 100 years ago. In recent 2 decades, it has been extensively studied under the framework of property testing. To be formal, the setting is as follows. We have some samples from 2 unknown distributions P, Q, over a domain of size K. Our algorithm needs to output accept if these 2 distribution constraints are the same, with probability larger than 2/3, and reject if the total variation distance between P and Q is larger than alpha, with probability larger than 2/3. The aim is to design a sample-efficient algorithms. A closely related problem is called identity testing. In this setting, we only have one unknown distribution P. We want to test whether P equals to a known distribution Q given some samples from P. If we assume that we can generate samples from the known distribution Q fourth grade, then we can reduce identity testing to closeness testing, where the distribution Q is also unknown. So, identity testing is not harder than closeness testing, and that implies a lower bound on sample complexity of identity testing is also a lower bound on sample complexity of closeness testing. Now I will give a brief introduction to differential privacy. A randomized algorithm is said to be differentially private if its output is stable for any 2 similar datasets. To be more formal, a randomized algorithm M is said to be epsilon delta differentially private if for all set S and all neighboring dataset XY, probability of Mx belonging to S is not larger than E2 epsilon times the probability of My belonging to S plus an additive term delta. As a result, an attacker cannot confidently infer whether a sample is in the input dataset given the output of this algorithm. And an algorithm is said to be epsilon differentially private if delta equals 0. When epsilon and delta decrease, the level of privacy increases. Closeness testing and identity testing under differential privacy constraints has been extensively studied by recent literatures. In these studies, noise is added to guarantee privacy. So, more samples are needed from these 2 distributions to achieve the same accuracy. And that can be seen as a cost of privacy. In all the previous studies, it is assumed that the privacy parameters for samples in P and samples in Q are the same. However, we see it as a problem because people often want to test whether 2 datasets comes from the same distribution, and these 2 datasets can come from different companies, different demographic groups, or even different countries subject to different legal requirements. So in many cases, these 2 datasets do not have the same privacy parameters, epsilon and delta. So our goal in this paper is to develop a closeness testing algorithm that guarantees epsilon 1 delta 1 privacy to the N1 users of the first group, and epsilon 2 delta 2 privacy to the N2 users of the second. One naive solution is to use the smallest privacy parameters for both datasets. However, it will cause a waste of resources. And our result shows that one can use fair samples from the less sensitive dataset to achieve the same accuracy. Now I will introduce the models. We studied 3 models in this paper: central, local, and shuffle differential privacy models. In the central model, users trust a central server to collect and analyze their data. So as shown in this graph, all these entities in the box are trusted, including this analyzer. And these X are the users, which hold their private data. The central server is responsible for adding some noise to the analyzed result to make users' data differentially private, and then publish it. In the local differential privacy model, users do not trust a central server and privatize their data locally. They privatize their data using a local randomizer R. This randomizer is responsible for adding some noise to the data and make the data differentially private before sending it to the analyzer. A third model is called shuffle differential private model. In this model, users trust a simple in-between entity called a shuffler to shuffle their private data and amplify the level of privacy. This shuffler can be done by using some multi-party computation primitives. And we have 2 shufflers here because we have 2 groups of data. It has been shown in previous studies that shuffling procedure can amplify local differential privacy. We study private coin protocols and public coin protocols in this paper. In private coin protocols, each user only has access to its own randomness. However, in public coin protocol, there also exists a common random seed, which is publicly available to everyone. And it has been shown in a previous study that one can leverage the common random seed to develop a more sample-efficient algorithm for identity testing under local privacy constraints. Now, I will give a brief introduction to the results. Let K denote the domain sets of P and Q. Our private coin algorithm under local privacy can use big O K2 3/2 divided by epsilon 1 square alpha square samples from the first group, and big O K 3/2 divided by epsilon 2 square alpha square samples from the second group. And this result is sample optimal. Namely, there is a matching lower bound, which has been proved in a previous paper. We also showed that we can leverage the common random seed to achieve a better sample complexity in public coin protocol. Particularly, we can reduce this K2 3/2 into K in the sample complexity. And this result in public coin protocol is also sample optimal. Here's our result for the shuffle privacy model. This result is actually a bit more complicated. So that's why we only show a simplified version here. Let's assume that epsilon 2 is smaller than epsilon 1, which means that the standard group is more sensitive to privacy. Then our algorithm only uses big O max K2 1/2 divided by alpha square, K2 3/4 divided by epsilon 1 alpha samples from the first group, and big O epsilon 1 square divided by big epsilon 2 square and 1 samples from the second group. We also showed that we can use fair samples in the public coin protocol. As for the central privacy, we get this result. And we obtain this result by combining a privacy amplification technique in differential privacy and a previous algorithm on the homogeneous differential privacy. Oh, and I forgot to mention that our result for the shuffle privacy model matches the best known upper bound for identity testing on the shuffle model. So we conjecture our result to be sample optimal. And for the central privacy model, we believe this result is far from optimal. And we leave some discussion in this paper for a better upper bound and leave it as a future work. Our results can be interpreted in two ways. If we wear privacy as a requirement, then our result quantify how much more data one needs to collect from the group with more stringent privacy requirements compared with the other group. So it's a multiplicative factor, which is epsilon1 divided by epsilon2 square on the local and shuffle privacy, and epsilon1 divided by epsilon2 on the central privacy. And if we wear privacy as a promise, our results showed that if more users from one group are willing to participate in the analysis, then we can guarantee better data accuracy, better data privacy for every user in that group. Now I will introduce the algorithms. Our algorithms on the local privacy is based on Hadamard response mechanism, and this mechanism is based on the following theorem. Let Hk be the k times k Hadamard matrix, where k is the smallest power of 2, which is larger than k. This small k is the domain size of the distribution P and Q. And let Cj be the locations of ones in the jth column of Hk, where j belonging to integers ranging from 1 to k. So a Hadamard matrix basically contains 0 and 1. And for any distribution P, let Pcj be the probability that a sample from P is in the set Cj. Then we have the following equation. The sum of the square of the difference between Pcj and Qcj equals to k divided by 4 times the square of L2 distance between P and Q. And the term on the left-hand side can be seen as the square of the L2 distance between two product Bernoulli distributions, whose parameters are determined by P, Q, and the Hadamard matrix HK. And by using the Cauchy-Schwarz inequality and the previous theorem, we can show the following. If the total variation distance between P and Q is larger than alpha, then the L2 distance between these two product Bernoulli distribution must be larger than alpha. And if P and Q are the same distribution, then these two product Bernoulli distributions must be the same. Motivated by this observation, a previous paper proposed an algorithm based on the Hadamard response. Before introducing that algorithm, we first introduce a very basic technique in differential privacy called randomized response. So if we have one bit of message and want to publish it, we can simply flip it with a certain probability. And this flipping will make sure this data becomes differentially private. And if we want to use the randomized response in local differential privacy model for closeness testing, we must compress the message of users. So recall that if user the data of each user generates from a sample from a distribution with domain size k. So that means each user hold a number which is an integer ranging from 1 to k. And if somehow we can compress this message of length log k into a message of length 1, then we can somehow use this randomized response mechanism to ensure the privacy. Motivated by this observation, this previous paper proposed this algorithm for identity testing on the local differential privacy constraints. First, they divide users from P into K disjoint groups with equal size. Then they assign the users in the J's group to a set Cj. This Cj are the location of ones in the J's column of the Hadamard matrix. Then each user generates a 1-bit message indicating whether the data of the user belonging to the set Cj. And then the user sends the bit to the server using randomized response. So basically the server will receive some samples from one product Bernoulli distribution. And it can calculate another product Bernoulli distributions because the distribution Q is known. And the server can decide whether to output accept or reject based on the L2 distance between these two empirical product Bernoulli distributions. This algorithm is actually very nice because the communication complexity is only 1 bit. So we want to generalize it to closeness testing on the heterogeneous differential privacy constraints. However, there is a problem. If users from P and Q uses randomized response with different privacy parameters epsilon1, epsilon2, then these two empirical distributions received by the server will not be the same even if P equals Q. To solve this problem, we design a L2 closeness testing algorithm on the heterogeneous local privacy constraints. After getting that tester, we are able to generalize their result. A set product of this is a new sample optimal L2 closeness tester for product Bernoulli distributions without privacy constraints. And to derive a public echoing protocol by leveraging the common random seed, we use the domain compression primitive. At a very high level, this technique hashes the domain of sets K into K prime, which is much smaller than K. And it preserves the total variation distance between probability distributions up to a shrinking factor of square root of K prime divided by K. Selecting the optimal value of K prime results in a sample optimal public echoing algorithm. That's all for local privacy model. Now I will introduce our algorithm for the shuffling DP model. A very common and natural idea to develop an algorithm on the shuffle privacy is to start from an algorithm on the local privacy and apply the amplification by shuffling result. This result has shown that if a local privacy algorithm satisfies some conditions, then the shuffling procedure can amplify the level of privacy. However, to use this approach, this algorithm on the local privacy needs to work reasonably well even for large privacy parameters. However, our algorithm on the local privacy constraints only works for high privacy regime. So we cannot directly use this amplification by shuffling result. Instead, we chose to use the distributed Poisson mechanism. By some calculation, we can show that the central server receives a sample from a mixture distribution P prime, combining P and the uniform distribution, a distribution Q prime, combining Q and the uniform distribution, if we let every user add Poisson noise to their data. Particularly, if we set N2, which is the number of samples from the second group, to be big theta epsilon1 divided by epsilon2 squared times N1, the total variation distance between P prime and Q prime, these two mixture distributions, will be proportional to the total variation distance between P and Q, which are the two original distributions. And in that case, we can use a known closeness testing algorithm to test the closeness between P and Q without privacy constraints. And by some calculation, we can get the desired bounds. And for the public keying protocol, we also used the domain compression technique to get a public keying algorithm. Okay, let me introduce our result for the central privacy model. For this model, we used a very basic technique called amplification by subsampling. So this lemma states that let A be epsilon 1 delta 1 differentially private algorithm, and H be a randomized mapping which uniformly chose N1 elements from N2 elements. Then the composition of these two mappings is epsilon 2 delta 2 differentially private, where epsilon 2 equals big O N1 divided by N2 epsilon 1, and delta 2 equals to N1 divided by N2 delta 1. So if this N1 divided by N2 is very small, then we can amplify this privacy by only selecting fair samples from a dataset. So namely, if a dataset has higher privacy requirements, we can start from more data and only select some of this data as the input for our algorithm. By combining this privacy amplification by subsampling technique and a previous algorithm on the homogeneous central privacy constraints, we can get the claimed bounds. However, these bounds should be far away from optimal. Okay, let me give a brief summary to our results. We obtain a sample optimal algorithm on the local privacy, and we conjecture our algorithm on the shuffle privacy is optimal. We also discussed several ideas for developing a better algorithm on the central privacy in this paper, which is not mentioned in this video. And that's all for this presentation. Thank you for watching this video.